You are now floating within the largest void in the observable universe. Scientists have just confirmed the existence of this structure using residual echoes from the Big Bang. This colossal cosmic void spans 2 billion light-years. The matter density in this region is nearly 20% lower than the cosmic average. This void surrounds our Milky Way galaxy. It encompasses every celestial body and galaxy you know. This colossal void has remained hidden in plain sight. It silently distorts our astronomical measurements. It is shattering our cosmological models describing reality. This suggests the true universe may be far stranger than we imagined. If you're ready to embark on this journey into the unknown, click that like button and let's dive deep into this cosmic mystery together. The universe is expanding. This is a fact repeatedly confirmed by observations. But just how fast the universe is expanding has become the most pressing question in contemporary cosmology. At the heart of this question lies a crucial number known as the Hubble constant. It describes the proportional relationship between the speed at which galaxies recede from us and their distance on a cosmic scale. Determining this value is one of the cornerstone tasks of modern cosmology. Scientists possess two fundamentally different, yet equally reliable measurement methods. Yet these two approaches point to divergent cosmic realities. The first method focuses on the universe's oldest light, the cosmic microwave background radiation, born when the universe was just 380,000 years old. This radiation emerged as the fiery, dense primordial plasma finally cooled enough to form neutral atoms. Photons previously trapped within the plasma were suddenly set free. These photons have since traversed the cosmos for 13.8 billion years, carrying primordial information from the early universe to our telescopes. By analyzing the minute temperature fluctuations within the cosmic microwave background, we can calculate the composition and evolutionary history of the universe with extraordinary precision. Projecting 13.8 billion years backward from this established physical model, we arrive at the expansion rate the universe should exhibit today. The European Space Agency's Planck satellite completed this measurement with unprecedented precision. It yielded a value for the Hubble constant of 67 kilometers per second per megaparsec. The second method focuses on the relatively nearby universe. Astronomers employ a technique known as the cosmic distance ladder. They first observe pulsating variable stars called Cepheid variables. These stars exhibit a strict correspondence between their pulsation periods and their intrinsic brightness. By measuring their pulsation periods and their apparent brightness as seen from Earth, astronomers can calculate the precise distance to their host galaxies. They then search these galaxies for another key celestial object, type Ia supernovae. These supernovae erupt when a white dwarf reaches its critical mass, and their peak brightness is remarkably consistent, making them the universe's standard candles. By calibrating type Ia supernovae in nearby galaxies using Cepheid variables, astronomers can extend this standard candle deep into the distant cosmos. They observe the apparent brightness of type Ia supernovae in the far universe, and combine this with the redshift of these supernovae spectra, the galaxy's recession velocity, to directly calculate the current rate of cosmic expansion. This research, led by Nobel laureate Adam Rees, yielded definitive results. The Hubble constant value is 73 kilometers per second per megaparsec. The discrepancy between the two results is 6 kilometers per second per megaparsec. This gap may seem insignificant, but within the precise framework of modern cosmology, it represents a catastrophic divergence. Both methods have undergone decades of refinement and development, with their measurement accuracy continuously improving. Yet this contradiction has not faded. Instead, it has sharpened as data becomes increasingly precise. Adam Rees himself has bluntly stated that as measurement accuracy improves, the tension persists. This stems not from simple experimental error. When the James Webb Space Telescope, the most powerful space telescope ever built, becomes operational, scientists hope it will reveal potential systematic errors in Hubble's measurements. The Webb telescope boasts higher resolution and sharper infrared vision. It can more clearly distinguish individual Cepheid variables within crowded galaxies. Yet the Webb telescope's observations delivered a decisive verdict. It fully confirmed the measurements of the Hubble Space Telescope. The high Hubble constant value measured locally is indeed accurate. This implies that some of our fundamental understandings may be flawed. Either our physical models of the early universe are flawed. The behavior of the early universe differs from our theoretical predictions, or our measurements of the local universe are being disrupted by some unknown factor, or even more peculiar physical processes await our discovery. Scientists have dubbed this discrepancy the Hubble Tension. But this term sounds too mild. Many leading cosmologists believe this is actually a fundamental crisis in cosmology. Our current best theory describing the universe is known as the lambda cold dark matter model. This model has successfully predicted and explained countless astronomical phenomena. It precisely describes the formation and distribution of galaxies. It perfectly matches the primordial abundances of light elements in the universe. It astonishingly predicted the temperature fluctuations in the cosmic microwave background radiation. Yet this powerful theoretical framework cannot reconcile these two different expansion rates. The statistical significance of the Hubble tension has surpassed the 5 sigma threshold. In particle physics, 5 sigma is the standard for declaring a discovery. This indicates a probability of only 1 in 3.5 million that such a discrepancy could arise purely from random fluctuations. Over the past decade, many researchers hoped this problem would resolve itself. They anticipated that more advanced instruments would uncover previously overlooked errors. They believed more data would eventually reconcile these two values. Yet reality has moved in the exact opposite direction. Each new observation, each more precise measurement, deepens the mystery. What could possibly cause the universe's expansion to exhibit two distinct speeds? The clues to the answer may not lie in distant deep space, nor in the universe's earliest moments. They might be hidden within the vast spatial structures surrounding us. A colossal cosmic structure we've only begun to comprehend is quietly influencing everything. Its existence compels us to rethink our place in the universe. It reveals a cosmos far more complex and fascinating than we ever imagined. Our journey ahead will traverse time and space, from the universe's first instant to the forefront of scientific inquiry. Together, we'll unravel this monumental puzzle that has perplexed top scientists for a decade. In the distant ages before galaxies, stars, or atoms existed, the universe was a boiling ocean of fiery, dense plasma. Photons, electrons, and protons were tightly intertwined, forming an opaque cosmic soup. Within this primordial soup, gravity and radiation pressure engaged in an eternal tug-of-war. Regions slightly denser than average would attempt to contract under their own gravity. Yet compressed regions generated immense radiation pressure. This force pushed matter outward. This perpetual tug-of-war created rhythmic oscillations. The early plasma universe resembled a drumhead struck by countless hands, generating spherical pressure waves traveling faster than half the speed of light. These were the universe's first sound waves. Imagine dropping a pebble into a tranquil pond. The ripples spread outward in perfect concentric circles. Now picture billions of stones hitting the pond simultaneously. Each stone generates its own expanding ring of waves. The early universe was such a rippling ocean. Only these ripples were pressure waves traversing plasma. They were not sounds any ear could hear. Their frequencies and intensities exceeded human perception. These waves carried normal baryonic matter, while dark matter, governed solely by gravity, remained anchored at each wave's origin. This state persisted for roughly 400,000 years, until the expanding universe cooled to a critical temperature, where electrons and protons could finally bind into stable neutral hydrogen atoms. This pivotal event is known as cosmic recombination. In that instant, the universe underwent a fundamental transformation. Photons, previously trapped by frequent collisions with charged particles, were suddenly liberated. The universe transformed from a murky soup into a clear, transparent expanse. The radiation pressure sustaining the sound waves abruptly vanished. All acoustic oscillations were instantly frozen in place, much like ripples on a pond frozen solid mid-motion. These frozen ripples persist throughout the cosmos to this day, stretched to immense scales by the universe's own expansion. They span billions of light-years of space. Today we call this eternal structure baryon acoustic oscillations. These oscillations left a permanent imprint on the distribution of matter. Galaxies tend to form at the peaks of these waves, making it more likely for galaxies to appear at specific distances from each other. This distance is the farthest these ancient sound waves could travel before freezing. When the universe was 380,000 years old, this characteristic distance was approximately 450,000 light-years. After 13.8 billion years of continuous cosmic expansion, the same distance has stretched to approximately 500 million light-years. Astronomers can measure this distance by counting thousands of galaxy pairs. They find a small but definite excess of galaxy pairs occurring at this 500 million light-year separation, compared to slightly closer or farther distances. This pattern is observed throughout the observable universe. This is direct evidence of baryon acoustic oscillations serving as the cosmic standard ruler. The marvel of this cosmic ruler lies in its absolutely fixed length. It is entirely determined by the physics of the early universe, the speed of sound waves propagating through primordial plasma, the temperature and density of the universe before atoms formed. These are precisely parameters we can determine by studying the cosmic microwave background, because we know exactly how long this ruler was when it was born. And since we can now observe this ruler in the distribution of galaxies across different cosmic epochs, we can measure how the universe has expanded over time. But what if this ruler appeared different in different places? If an observer were situated in a special region of space, the structure of that region would distort the pattern the ruler displays. And this is precisely the startling fact scientists discovered while analyzing data. By counting galaxies in every direction accessible to telescopes, astronomers uncovered a serious problem. Within a billion light-years of Earth, the number of galaxies was significantly fewer than expected. Light from more distant regions, those beyond 15 billion light-years, revealed galaxies within a unit volume were 50% brighter and denser than those near us. Imagine living in a suburban house. When you gaze at the night sky, most of the brightness comes from distant cities rather than nearby neighbors. This is the cosmic situation we find ourselves in. We seem to reside in the cosmic suburbs, where the glow of distant cities masks the local sparseness. This pattern first became apparent in 2013. Astronomers Ryan Keenan and Amy Baggins analyzed 35,000 galaxies from multiple sky surveys. They noted a disturbing phenomenon. Matter density drops significantly as you approach our location. This effect is not insignificant. Measurements indicate our surrounding region is 15 to 50% less dense than the cosmic average. They named it the KBC Void after their initials. Some scientists prefer calling it the local void. This term sounds less technical, yet more unsettling. The scale of this void is immense. It spans approximately 2 billion light-years. This equates to 6.6 trillion parsecs in astronomical units. By comparison, our local group, comprising the Milky Way and Andromeda galaxies, with a diameter of roughly 10 million light-years, is 200 times smaller than this void. Even our supercluster, Laniakea, with its 500 million light-year diameter, is entirely enveloped within this colossal void. Yet voids are not entirely empty. They represent regions of relatively sparse galaxies, not absolute void. Within a given volume, you might find only 50 galaxies instead of 100. Matter still exists, but it is distributed more sparsely. Our local hole encompasses most of the Milky Way, the local group, and the Laniakea supercluster. It contains over 100,000 galaxies. Yet compared to the average density of the universe, we truly reside in a relative desert. The crucial point is that the Milky Way is not located at the edge of the void, but rather near its center. This position is critical. If we were at the void's edge, the distribution of galaxies we observe would be highly asymmetrical. Instead, the lack of density surrounds us fairly uniformly from all directions. Multiple independent surveys, including optical, infrared, X-ray, and radio bands, have confirmed this structural pattern. Fewer galaxies nearby, more in distant directions. The distribution of galaxies does not lie. How could such an immense region of low density exist? What does it mean for our observations of the universe? Imagine removing 1/5 of the matter around you. 1 in every 5 galaxies vanishes. 1/5 of the dark matter is nowhere to be found. This is the reality of living within the KBC void. On cosmic scales, this disparity represents a staggering loss of mass. To grasp its significance, we must consider the gravitational force binding the universe together. Every particle of matter attracts other particles. Regions of dense matter possess stronger gravity, pulling more matter toward themselves, and growing increasingly dense. Regions of sparse matter have weaker gravity, causing matter to drift toward stronger gravitational fields. Over time, voids become increasingly empty. This process has been ongoing for nearly 14 billion years. A 20% density deficit in KBC voids produces specific measurable effects. First is the gravitational potential. Dense regions form valley-like gravitational potential wells. Low-density regions form gravitational potential hills. Objects naturally roll down hills. In space, this means galaxies flow from low-density regions toward high-density regions. Voids act like giant hills, pushing everything away from their centers. Second is the local expansion rate. Space itself expands uniformly everywhere, but local gravitational effects make certain regions appear to expand faster or slower. Inside voids, less matter means gravity slows expansion less effectively. The reduced density allows space to expand more freely. This creates a noticeable acceleration in the local expansion rate. For galaxies within voids, these density effects are real. When we measure the recession velocity of nearby galaxies, we are measuring the expansion within this low-density bubble. These measurements do not represent the average expansion rate of the universe. They represent the expansion rate at a specific location. It's like measuring the temperature in Death Valley and concluding Earth is hotter than expected. In reality, you're just standing in an exceptionally hot spot. We may have done something equivalent in measuring cosmic expansion. The root of the controversy lies in our standard cosmological model, the lambda cold dark matter, LCDM, model. This model predicts the universe should be fairly uniform on large scales. Of course, tiny fluctuations exist. Galaxies cluster together to form superclusters. But the average density on scales of hundreds of millions of light-years should be roughly the same everywhere. A structure 20 billion light-years wide with 20% lower density should not exist within the standard cosmological framework. The probability of such a structure forming randomly is extremely low. Some calculations suggest this probability is as low as 1 in a billion. Yet observations clearly indicate we reside within a low-density region. Multiple independent measurements confirm this finding. Therefore, we either inhabit an exceptionally rare location by sheer misfortune, or our cosmological model is incomplete. A third possibility exists. Perhaps seemingly rare structures are actually quite common. Our model underestimates the clumpiness of the universe. The cosmos may be far more textured than we imagined. Voids are not static, they evolve. Evolution implies emptying. The process unfolds thus. A void's density is lower than its surroundings. The stronger gravitational pull of the surrounding regions reaches into the void, pulling everything inside outward. Galaxies near the void's edge experience the strongest effect. They accelerate toward denser regions outside the void. As they depart, the void becomes slightly emptier. The gravitational imbalance intensifies, causing more matter to flow outward. This creates a runaway effect. Voids expand and deepen over cosmic time. Scientists call this process void evacuation. Since the early universe, every billion years more matter drifts from low-density regions into overdense structures. This flow occurs at tremendous speeds. Studies show galactic stream velocities can exceed 400 kilometers per second, across distances of 300 million light-years. These are not random motions, but coordinated flows, like rivers of galaxies cascading down the cosmic gravitational landscape. Our own Milky Way galaxy is caught up in this flow. We are hurtling out of the void center at nearly 1 million miles per hour, equivalent to 250 kilometers per second. We are escaping from the heart of this local void. This outward motion profoundly impacts measurements of expansion. When we observe a galaxy and measure its redshift, we see two effects combined. The first is the cosmic expansion itself stretching the space between us and the galaxy. The second is the galaxy's proper motion velocity through space. This can increase or decrease the redshift, depending on the direction of motion. Within the void, most galaxies are moving outward. This means that in most directions, the redshift of galaxies includes an additional component contributed by the void's dispersion. Their total redshift is slightly higher than that produced by cosmic expansion alone. When cosmologists measure the Hubble constant using nearby galaxies, the measured redshifts are affected by void dispersion. This makes the measured expansion rate appear higher than the actual value. Nurbane at Andreas University has precisely calculated this effect. His model shows that KBC voids can inflate the locally measured Hubble constant by about 11%. The math is straightforward. If the true expansion rate is 67 kilometers per second per megaparsec, and the void effect adds 11%, you get roughly 74, which aligns almost perfectly with the locally measured 73. But this explanation only holds if our position is near the void center. If we were at the void's edge, the effect would be asymmetric. We'd observe enhanced expansion in certain directions and normal expansion in others. Yet measurements show the enhancement is fairly uniform across all directions. This strongly suggests we reside within hundreds of millions of light-years of the void center. What are the odds of this? Living within a rare giant void is already improbable. Living near its center is even more suspect. Unless voids are far more common than we imagine, or the central location itself possesses some peculiarity making it more likely to harbor observers. This argument from anthropic principle makes some scientists uncomfortable, but data doesn't care about our comfort. Consider this analogy: standing on an airport moving walkway. People approaching you appear faster than their actual walking speed. The walkway increases their perceived velocity. Measuring cosmic expansion from within space follows a similar principle. The dynamic effects of the void amplify the observed expansion rate. Every measurement reveals something about reality, but interpreting these measurements requires contextual understanding. When Henrietta Leavitt discovered the period luminosity relationship for Cepheid variables, she gave astronomers a cosmic measuring rod. When Edwin Hubble used this rod to detect cosmic expansion, he measured the universe's global behavior. But when modern astronomers use this rod to measure a high Hubble constant, they may be measuring the unique dynamics of our local space. The space inside the KBC void is indeed expanding at a faster rate. This expansion is real, but it cannot represent the entire universe. It's like measuring rainfall in a desert and concluding the Earth is dry, or taking temperatures at the South Pole and declaring the Earth is frozen. Local conditions matter. Here's the situation. As light from distant galaxies travels toward us, spatial expansion stretches its wavelength. This is cosmological redshift. The extent of stretching reveals how much space expanded during the light's journey. Greater expansion means larger redshift. By comparing redshift and distance, we calculate the expansion rate. But within the void, a complicating factor exists. Our Milky Way isn't receding solely due to cosmic expansion. It's also moving through space, escaping this void. This motion itself contributes to redshift. Separating these two effects is nearly impossible with current technology. Astronomers typically assume all redshift stems from cosmic expansion. They plug measured values into formulas to calculate the Hubble constant. Thus, they arrive at 73 instead of 67. This discrepancy seems mysterious, but isn't. The dynamics of the void disguise it as accelerated expansion. Nelbanek clearly explains this using the concept of gravitational potential. Imagine the universe as a landscape. Valleys are dense regions, voids are hills. Galaxies roll from hills into valleys. Their motion is descent, not expansion. But redshift cannot distinguish descent from expansion. Both stretch light wavelengths. The only way to detect this effect relies on statistics. If you measure enough galaxies in enough directions, patterns emerge. The sparse distribution of voids creates a systematic bias. All nearby measurements are slightly elevated. At very distant scales, this effect vanishes because it lies beyond the edge of the voids. This is precisely what observations show. The Hubble tension exists in low redshift measurements. These measurements sample our local region, while high redshift measurements sample the distant universe, where the tension vanishes. The cosmic microwave background originates from all corners of the universe. It represents the average across the entire observable universe. CMB measurements reveal the true average expansion rate. Local measurements show the expansion rate within our own region of space. Both are correct, they simply measure different things. But accepting this explanation requires embracing an unsettling truth. We live in a special place, not in a philosophical sense, but in a measurement sense, systematically different from the cosmic average. This makes cosmology more difficult. We cannot simply assume our backyard represents the entire universe. When interpreting data, we must account for local peculiarities. Some scientists oppose this conclusion. They favor explanations involving new physics, such as early dark energy or modified gravity theories. These explanations are possible, but typically more complex. They require introducing new phenomena or particles. The void hypothesis, however, employs only known physics. Gravitational density variations, spatial motion, all are standard and well understood. Occam's razor suggests simpler explanations deserve serious consideration. Science is about probability. When evidence overwhelmingly supports one interpretation, we should adopt it. The KBC Void hypothesis has now crossed that threshold. 2 decades of data, hundreds of measurements. Detections of baryon acoustic oscillations spanning vast space and time. All point to the same conclusion. We inhabit a low-density bubble. Statistical analysis is decisive. Researchers compared 2 models. The standard model of a homogeneous universe, and a model incorporating local voids matching KBC void characteristics. They asked, which model better explains the observed baryon acoustic oscillation data? The answer is unequivocal. The model incorporating voids has a probability of matching the data 100 million times higher than the uniform model. This is not a typographical error. Scientists denote this as 10 to the power of 8. In everyday terms, this means the evidence is overwhelming. By comparison, particle physicists require a 5 sigma significance to claim a discovery. 5 sigma corresponds to a random probability of approximately 1 in 1.35 million. The evidence for voids far exceeds this standard by several orders of magnitude. This conclusion stems not from a single measurement, but from decades of combined observations. Galaxy redshift surveys mapping 3-dimensional structure. Measurements of galaxy clustering at different cosmic epochs. Measurements of baryon acoustic oscillation angular scales at various distances. Galactic proper velocities indicating body flows. Each dataset independently suggested an undercount of local density. Together, they became irrefutable. Most strikingly, the analysis process did not presuppose the existence of voids, and then seek supporting evidence, which would introduce confirmation bias. Instead, researchers utilized all available baryon acoustic oscillation measurements from multiple surveys, spanning over 2 decades of data. They fed the data into models, allowing the models themselves to determine whether incorporating voids improved the fit. The improvement was dramatic. Models without voids struggled to match observations. Galaxy distributions deviated from predictions. The cosmic distance ladder showed systematic discrepancies. Expansion measurements varied by location in ways standard cosmology couldn't explain. But once voids were incorporated, everything fell into place. The model accurately predicted galaxy clustering patterns. It explained the Hubble tension without invoking new physics. It aligned with measurements of matter flowing toward void edges. Of course, statistical possibility is not certainty. Science never provides absolute proof. There is always room for alternative explanations. Perhaps multiple unrelated systematic errors coincidentally produced the appearance of voids. Maybe dark matter behaves differently than we imagine. Or dark energy varies with location. Or quantum effects operate on cosmic scales. All these possibilities exist, but their likelihood is far lower than the explanation that we simply live within a void. The evidence is now sufficiently compelling that ignoring it would require rejecting standard statistical inference methods. Some researchers are doing just that. They point out that the lambda cold dark matter model predicts such large voids should be extremely rare. Finding ourselves within one seems too coincidental. This is sometimes called the fine-tuning problem. But rare is not impossible. Rare events do occur. People win lotteries despite extremely low odds. Planets form in unusual orbits. We may simply be observers living in such an unusual place. After all, observers can only exist where conditions permit their existence. If voids somehow favor galaxy formation or the habitability of life, it would be unsurprising for intelligent observers to emerge there first. This anthropic reasoning makes some scientists uncomfortable, but it is not unscientific. For the past decade, the Hubble tension has been cosmology's most perplexing problem. 2 methods, 2 answers. a discrepancy of 9 kilometers per second per megaparsec. Countless scientific careers have been spent hunting for errors. Precision instruments built to resolve the discrepancy only deepened the contradiction. Theoretical physicists proposed bizarre solutions, from early dark energy to varying fundamental constants, from modified gravity to quantum vacuum fluctuations. Each proposal grew more complex than the last, and they may all be unnecessary. The void offers an elegant solution. It requires no new physics. Consider what each method actually measures. The cosmic microwave background method observes ancient light from the universe at 380,000 years old. This light arrives simultaneously from all directions, sampling the entire observable universe. Its temperature fluctuations encode information about the universe's density composition and expansion history. Cosmologists use this data, plugging it into the lambda cold dark matter equation, and projecting forward 13.8 billion years. The model predicts today's expansion rate should be 67, a global average representing the entire universe. The local method employs entirely different physics. By observing Cepheid variables in nearby galaxies to establish a distance scale, and then measuring type Ia supernovae in these galaxies to calibrate their absolute brightness. Next, it observes more distant supernovae, calculating their distances using apparent brightness, combined with redshift measurements showing the receding speeds of these galaxies. Distance and velocity together yield the Hubble constant. This method gives 73. But there's a crucial detail. This method primarily samples nearby space. The Cepheid variables used for calibration can only be clearly observed within 100 million light-years. Type Ia supernovae used for measurement extend to 2 to 3 billion light-years. This distance range lies entirely within the KBC Void. The local method measures expansion within the void. The cosmic microwave background method measures the average expansion across all regions. They measure different physical quantities. Imagine measuring the average human height. One scientist measures every person in the Netherlands, known for its tallest average height. Another scientist analyzes global census data. The former finds 183 centimeters, the latter 171 centimeters. Both measurements are correct. They simply measure different populations. This is the essence of the Hubble tension. It's not a contradiction or crisis, just a difference between local and global measurements. The void explains why local measurements appear elevated. Galaxies in sparse space exhibit enhanced redshifts. Less matter implies slightly faster local expansion. Gravitational gradients cause systematic bias. Banach's calculations show the magnitude of the effect aligns almost perfectly with observations. An 11% increase in the Hubble constant would raise 67 to 74, exactly matching local measurements. Some details require refinement. The precise size and density distribution of the void demand finer mapping. The Milky Way's position relative to the void's center requires more accurate determination. Alternative explanations need rigorous comparison, but the fundamental mechanism is clear and testable. If the void explanation is correct, we can make specific predictions. Measurements beyond 3 billion light-years should show a lower Hubble constant value. Approaching 67. Hubble tension should vanish at extreme distances. Observations should reveal directional asymmetry since the void structure is not perfectly spherical. Volume flow should align with the void's dispersion pattern. These predictions can all be tested by next-generation sky surveys. The James Webb Space Telescope will observe Cepheid variables at greater distances. The Vera Rubin Observatory will map billions of galaxies with unprecedented detail. The Euclid Space Mission will measure acoustic oscillations spanning cosmic history. Within a decade, data will either confirm or falsify the void hypothesis. If confirmed, the Hubble tension will not culminate in the discovery of exotic physics. There will be no revolutionary new particles or forces. It will simply recognize the importance of location. Measuring the universe from within the void distorts the results. We must account for local structure when interpreting observations. This may be humbling. We are not in a typical location. We occupy a statistically unusual spot. This makes cosmology more complex. But at least it doesn't require rewriting the foundations of physics. You cannot directly see this vast cosmic void. It is defined by absence. No luminous markers outline its contours. No dark curtains mark its boundaries. Astronomers perceive it by calculating what is present and noting what is missing. This technique is remarkably sophisticated. It requires surveying millions of galaxies across billions of light years. It demands precise measurements of position, distance, and velocity. It involves statistical analysis of vast, complex datasets. But this approach does work. The first method for mapping voids is galaxy counting. Astronomers measure large volumes of space, dividing them into countless equal-sized cubic regions. They then count the number of galaxies within each cube. Most cubes contain similar numbers of galaxies. Some cubes contain more galaxies, forming galaxy clusters and superclusters. Some cubes contain slightly fewer. But occasionally, you'll find cubes with far fewer galaxies than average. Connect these low-density cubes in space, and you discover a void. This method revealed the first cosmic void in 1978. As galaxy surveys progressed, the cosmic Webb structure became clearer. Dense filamentary structures crisscross space. Where filaments intersect lie massive galaxy clusters. Voids occupy the vast spaces between these filaments, like bubbles within foam. The structure of the KBC Void began emerging around 2013 from multiple survey datasets. Several large-scale observational projects contributed data to the discovery of the KBC Void. The 2-degree field galaxy redshift survey measured the positions and distances of hundreds of thousands of galaxies. The Sloan Digital Sky survey mapped a broader cosmic canvas with greater precision. The 2-micron all-sky survey provided complementary insights by penetrating dust through infrared wavelengths. Each survey revealed identical patterns. Galaxy density decreases markedly outward from the Milky Way. The second approach involves tracking galaxy motion. Each galaxy's velocity comprises 2 components. The first is recession velocity proportional to distance, driven by cosmic expansion. The second is proper motion, generated by gravitational interactions, typically hundreds of kilometers per second. By measuring the total velocity and subtracting the expected expansion velocity, astronomers can isolate proper motion. These proper motions reveal the distribution of gravity. Galaxies flow from regions of low density toward regions of high density. This large-scale, coherent motion is called bulk flow. It indicates that immense mass structures are tugging on vast spaces. The Cosmic Flow 4 catalog tracks the motion of tens of thousands of galaxies. The data reveals systematic flow patterns that align perfectly with predictions of void dispersion. Galaxies near the void's edge are moving outward faster than pure expansion would dictate. Galaxies in intermediate regions show weaker outward motion. This pattern matches predictions for a void with a radius of approximately 1 billion light-years. The third method employs baryon acoustic oscillations as a cosmic ruler. These frozen sound waves from the early universe create a characteristic distance scale in the distribution of galaxies. By measuring how this scale behaves at different distances and cosmic epochs, astronomers can chart the history of cosmic expansion. But the key lies in how local voids distort the performance of the baryon acoustic ruler. Void dynamics introduce an additional component to galaxy redshifts, making galaxies appear farther than they truly are. This alters the apparent baryon acoustic oscillation scale in a predictable manner. We now possess 2 decades of baryon acoustic oscillation measurements from multiple surveys across different wavelengths, optical observations by ground-based telescopes, and infrared data from space missions. Each dataset independently reveals this distortion, consistent with our local underdensity. The fourth method examines the integral Sachs-Wolf effect. Photons in the cosmic microwave background gain or lose energy when traversing gravitational potentials. When a photon enters a dense region, it must expend energy to climb out of the gravitational potential well, causing redshift. When a photon enters a void, it gains energy sliding down the gravitational potential hill, causing blue shift. In a static universe, these effects would cancel each other out. However, the universe is expanding and gravitational potentials evolve over time. This results in net energy changes that leave imprints on the cosmic microwave background. Massive voids create cold spots in the cosmic microwave background. Local voids should produce such cold spots in our direction of motion. Observational data suggest the existence of these features, though they remain uncertain. Finally, the gravitational lensing effect. Mass bends spacetime, causing light to propagate along curved paths. By measuring the time delays between multiple images from the same background source, astronomers can map the distribution of mass. Smaller voids produce weaker lensing effects, while also generating specific distortion patterns in background galaxy images. These patterns are extremely faint, requiring measurements across thousands of square degrees of sky with high resolution. Future missions like Euclid and the Vera Rubin Observatory will provide this critical data. Together, these methods paint a consistent picture. Our local universe harbors a significant density deficit. This low-density region extends outward for approximately 1 billion light-years. It influences galaxy motion, clustering patterns, and fluctuations in the cosmic microwave background. This is neither a measurement error nor the product of a single technique. It is a genuine physical structure, confirmed by multiple independent observations. This immense structure is known as the KBC Void, named after the 3 astronomers who discovered it, Keenan, Bott, and Coyle. Its scale is awe-inspiring, spanning 20 billion light-years from edge to edge, meaning it would take 20 billion years to traverse it even at the speed of light. To grasp this scale, consider some comparisons. Our local group, comprising the Milky Way and Andromeda galaxies, has a diameter of about 10 million light-years. The KBC Void is 200 times wider. Our local Laniakea supercluster has a diameter of about 500 million light-years. This void is 4 times wider than that. It is one of the largest structures in the known universe. But this void is not absolute emptiness. It clearly contains our own Milky Way galaxy. It encompasses most of the local group and the Laniakea supercluster. It holds over 100,000 galaxies within its confines. Yet compared to a typical cosmic region of equal volume, its matter density is 15 to 50% lower. The exact value depends on the specific location measured. Near the center, the density may be 40% below the cosmic average. Near the edges, it might be only 20% lower. This density gradient is crucial for understanding the void's dynamics. A steeper gradient implies stronger gravitational pull from outside. Matter accelerates its escape, and local expansion rate distortions become more pronounced. Precisely mapping this gradient will help quantify the void's influence on the Hubble constant. The critical question lies in our position within the void. The Milky Way is not situated at the void's edge, but within hundreds of millions of light-years of its center. This central location is pivotal. If we were at the edge of the void, the distribution of galaxies we observe would be highly asymmetrical. We would see fewer galaxies toward the void's center, and more toward the outer universe. Yet observations show the density deficiency surrounds us fairly uniformly from all directions. This evidence of isotropy strongly supports our proximity to the void's center. This central location also explains why the void's effects uniformly influence our measurements. If we were at the edge, Hubble tension would be pronounced in some directions and weaker in others. Yet actual measurements show the expansion boost is roughly equal in all directions. This aligns with expectations for being near the center of an approximately spherical void. So how did such an immense region of low density form? Its formation history is complex and lengthy. Standard cosmology posits that voids originate from tiny density fluctuations in the early universe. At the universe's inception, quantum fluctuations were amplified by cosmic inflation, leaving behind minute density inhomogeneities, some regions slightly denser, others slightly sparser. These fluctuations were random, like static on an old television screen. Under gravity's influence, these fluctuations amplified. Slightly denser regions exerted stronger gravity, attracting more matter and growing denser. Slightly less dense regions possessed weaker gravity, allowing matter to flow outward, becoming increasingly sparse. This fundamental process of gravitational instability shaped the cosmic structure. During the first few billion years, the densest fluctuations collapsed to form the first generation of stars and galaxies. Their gravity attracted surrounding gas, causing galaxies to cluster together into galaxy clusters. Galaxy clusters connected by filaments, while voids grew between these filaments. Voids themselves evolve over time. A young void may contain numerous scattered galaxies. Under the pull of surrounding gravity, these galaxies slowly drift toward the void's edges. The void's interior gradually empties. Over time, the void grows larger and more hollow. Most galaxies migrate toward the boundary, and some even escape the void entirely. The contrast in density between the void's interior and surrounding regions becomes increasingly pronounced. The KBC Void appears to be a mature, ancient void. It has been growing throughout most of cosmic history. Its size indicates it originated from a large-scale fluctuation in the early universe. In the standard lambda cold dark matter model, structures grow from the bottom up. Small-scale structures form first and gradually merge into larger ones. This naturally creates voids as the space between collapsing regions. But growing into a void as large as KBC requires special initial conditions. The initial fluctuations must have been exceptionally large. Randomness occasionally produces such large-scale fluctuations. Quantum fluctuations during inflation created variations across all scales. Most fluctuations were minor, but large-scale fluctuations occasionally emerged. Another possibility is that our cosmological models require adjustment. Perhaps the lambda cold dark matter model underestimates structure formation at the largest scales. Perhaps initial conditions were more turbulent than we assumed. Modified gravity theories like MOND, while explaining certain observations, also predict larger voids. But regardless of the specific mechanism, voids are natural products of cosmic structure formation. The question isn't whether voids exist, but whether voids as large as the KBC should exist, and whether our finding ourselves within it is mere coincidence. The Milky Way doesn't float in isolation within this void. We are part of a larger structure, the local sheet. This is a flat, extended gathering of galaxies spanning hundreds of millions of light-years. Its shape resembles a pancake, thin in one dimension, yet broad in two. Dozens of galaxy groups and clusters inhabit this region. The local sheet forms a boundary within the KBC void, a smaller structure. This arrangement reveals how structures form. Voids grow by ejecting matter toward their edges. That matter doesn't vanish. It accumulates at boundaries, forming sheet-like and filamentary structures. The local sheet is such an accumulation zone. Matter that once filled the local void is now concentrated within this sheet. Measurements show the local sheet is moving away from the void center at a considerable speed of 260 kilometers per second. This outward motion results from the void's dispersal. The entire sheet contains thousands of galaxies and billions of stars that were once part of the void. However, the sheet does not move uniformly as a whole. Different sections have varying velocities. Gravitational interactions with neighboring structures create complex motion patterns. Consequently, this region is stretched and distorted during the evacuation process. Over time, it may fragment. Individual galaxy groups will follow their own trajectories. Some will join nearby superclusters, while others drift into intergalactic space. Billions of years from now, the local sheet may no longer be a coherent structure. The cosmic velocity field reveals our motion within the void. Our Milky Way is not merely orbiting within the local group. The entire local group participates in the local sheet's overall motion. We are carried along as it escapes the local void. This motion affects how we measure cosmic expansion. When we observe a galaxy and measure its redshift, we are actually comparing its velocity to ours. But our velocity incorporates the local sheet's dispersal flow. This introduces systematic bias into expansion measurements. Galaxies in our direction of motion exhibit a slight blue shift, relative to what pure expansion would predict, while those in the opposite direction show a slight red shift. Averaging these biases across all directions might partially cancel them. But if measurements favor certain directions, residual biases remain. Careful analysis must account for the local sheet's motion. Fortunately, we can measure this motion by observing the cosmic microwave background. Our motion relative to the CMB produces dipole modes. The direction of our motion is slightly hotter, while the opposite direction is cooler. This measurement indicates the local group is moving at 630 kilometers per second, relative to the cosmic reference frame. This velocity incorporates the local sheet's body flow within the void, plus contributions from larger structures like the Laniakea supercluster. Subtracting these components allows astronomers to correct for the effects of local peculiar motion in expansion measurements. However, as the void's boundaries are defined with greater precision, these corrections are continually improving. The dynamics within the void profoundly influence cosmological measurements. When we measure the recession velocities of nearby galaxies, we are measuring the expansion within the void. This expansion is amplified by missing matter and gravitational potential hills. It does not represent the average cosmic expansion rate. It represents the expansion rate at a specific location. It's like measuring the temperature in Death Valley and concluding Earth is hotter than expected. In reality, you're just standing in an exceptionally hot spot. We may be doing something equivalent in measuring cosmic expansion. Accepting our position near the center of a void requires accepting a humbling truth. We are not in a typical place. We are in a statistically unusual region. This complicates cosmology. We cannot simply assume our backyard represents the entire universe. When interpreting observations, we must account for local peculiarities. This isn't a retreat to geocentrism, but a recognition that even in a homogeneous universe, fluctuations are inevitable, and we happen to be within one. Science's goal is to understand reality, however unusual it may appear. The portrait of the KBC Void reveals a universe more complex and fascinating than we imagined. The Hubble Tension stands like a blinding warning light, flashing at the heart of contemporary cosmology's grand edifice. It forces scientists to confront a fundamental choice. Should we explain this anomaly using known physics? Or must we resort to unknown new physics to solve the puzzle? The KBC Void hypothesis offers an elegant and economical path, standing firmly on the side of known physics. The charm of this path lies in its strict adherence to Occam's razor. Entities should not be multiplied beyond necessity. It requires no postulation of undiscovered particles or forces. It demands no modification of gravitational laws or the nature of dark energy. It merely points out that we have consistently overlooked our true position within the universe, and how this specific location systematically distorts our measurements. All physical components employed in the void interpretation are readily available and thoroughly validated. General relativity describes how matter and energy warp spacetime, and how variations in gravitational potential cause matter flows and changes in local expansion rates. The cosmological principle itself permits fluctuations on small scales, but we underestimated the magnitude these fluctuations could attain. Incorporating the KBC void and its dynamical effects into our model is akin to finally recognizing the source of systematic error when analyzing a complex experiment. Once you correctly identify and calibrate this local effect, the seemingly contradictory measurements miraculously converge. The 67% from the cosmic microwave background represents the average expansion rate across the entire universe, while the 73% from local measurements reflects the expansion rate within our low-density bubble. Both are correct. They measure distinct physical realities at different scales. By contrast, explanations from new physics appear convoluted and contrived. To explain this 6 km/second discrepancy, theorists have proposed a variety of hypotheses. The early dark energy hypothesis posits an additional dark energy component in the early universe, which briefly emerged shortly after the Big Bang, altering the initial expansion history, before fading away without a trace. Modified gravity theories attempt to adjust Einstein's general relativity, assuming gravity behaves differently on cosmic scales than what we observe on Earth and in the solar system. Dark energy proposals suggest its intensity is not constant but evolves over time, and may even vary with spatial location. Other more exotic ideas include interactions between dark matter and dark energy, effects from extra dimensions, and the emergence of quantum gravity effects. Each of these proposals requires introducing new free parameters, and each demands fine-tuning to match partial observational data. A more severe problem is that many of these new physics models often undermine other well-established fits while resolving the Hubble tension. They may predict cosmic microwave background fluctuation patterns inconsistent with observations. They may cause galaxy formation and distribution theories to conflict with actual surveys. They may fail to explain the matter distribution observed through gravitational lensing. The strength of the standard lambda cold dark matter (CDM) model lies precisely in its ability to explain a vast array of diverse observational phenomena within a single, simple framework. Most new physics explanations, however, resemble robbing Peter to pay Paul. The void interpretation avoids this problem entirely. It fully preserves the core framework of the lambda cold dark matter model, while more honestly acknowledging that our local environment is not a typical cosmic sample. It is not a replacement theory, but a supplement and refinement to existing theories, a more nuanced interpretation of observational data. Yet embracing the void explanation compels us to confront a deeper philosophical challenge. The cosmological principle, a core tenet guiding our cosmic understanding since Copernicus, asserts that the universe is homogeneous and isotropic on large scales. It posits no center, no privileged location. The existence of the KBC Void and our position within it seem to flagrantly violate this principle. A structure spanning 2 billion light-years with 20% lower density is clearly not a minor fluctuation on such a vast scale. It compels us to reconsider at what scale uniformity actually begins. This raises a profound question known as the anthropic principle. Why do we happen to live within such a vast void? Is this merely an extremely unfortunate coincidence? Or does this environment somehow favor the emergence of intelligent life? Perhaps in regions of excessive density, galaxy mergers occur more frequently. Violent activity makes planetary systems unstable. Intense radiation would stifle the budding of life. Conversely, regions with too low density might fail to produce sufficient heavy elements for building planets and sustaining life. Our own niche, situated in this moderately low-density zone, may well represent the cosmic golden mean capable of nurturing observers. If this holds true, then our discovery of ourselves within a void is not a coincidence requiring explanation, but an inevitable outcome. Intelligent observers can only exist within environments that permit their existence. This reasoning unsettles some scientists, as it appears tinged with teleology. Yet its statistical version is rigorous. It merely indicates that when interpreting observational data, we must account for a filtering effect, namely, our very existence as observers already imposes constraints on the cosmic environment we can observe, whether one accepts the anthropic principle or not. Evidence for the KBC Void demands we revise our understanding of the cosmological principle. Perhaps the principle remains broadly valid, but the scale of uniformity it describes is vastly larger than previously assumed. Perhaps the universe is homogeneous on scales of billions of light-years, yet exhibits significant fluctuations within our observable universe. Our cosmos may resemble a loaf of bread with marble-like patterns, uniform in overall composition, yet rich in local texture and structure. If we embrace the void interpretation, we can paint a new, self-consistent cosmic picture. In this picture, all seemingly contradictory observations find their place. The cosmic microwave background radiation remains our Rosetta Stone for exploring the early universe. The physical laws and initial conditions it reveals remain valid. The global Hubble constant of 67 derived from it serves as the baseline for cosmic expansion. Local supernova and Cepheid variable star measurements remain precise and reliable. They authentically reflect the expansion state of our local region. This region, with sparse matter and weaker gravitational constraints, allows space to expand more freely, resulting in higher measured expansion rates. Baryon acoustic oscillations measurements serve as a bridge connecting the global and local scales. In the distant, high-redshift universe, they exhibit standard scale, validating predictions from the cosmic microwave background. In nearby low-redshift regions, they exhibit systematic distortions, clearly indicating the dynamical effects of voids. Observations of galaxy stream flows act as cosmic wind vanes, directly revealing the spectacular outflow of matter from void centers. All these independent clues weave into a coherent web of evidence, pointing to a single conclusion. This conclusion not only resolves the Hubble tension, but also offers a fresh perspective on the large-scale structure of the universe. It suggests the cosmic web may be more extreme than simulations indicate, with larger, emptier voids and denser, more massive galaxy clusters than anticipated. This provides new constraints for understanding the nature of dark matter and dark energy, and may influence predictions about the ultimate fate of the universe. Of course, science demands falsifiability. The void hypothesis makes explicit and bold predictions. These predictions will soon be tested by next-generation astronomical observations. If we are correct, the Hubble tension should be a local phenomenon. When we use instruments like the James Webb Space Telescope to measure galaxies far beyond the KBC Void, the calculated Hubble constant should gradually decrease and approach 67. The Euclid Space Telescope and the Vera Rubin Observatory will map billions of galaxies in 3 dimensions with unprecedented precision. These maps should clearly reveal the void's boundary, along with its unique internal density gradients and galaxy flow patterns. More precise measurements of the integrated Sachs-Wolf effect in the cosmic microwave background should detect cold spots corresponding to the void in our direction of motion. If these predictions are confirmed, a crisis in cosmology will be resolved, without requiring revolutionary new physics, only a clearer understanding of our place in the universe. If these predictions are disproven, the void hypothesis will be discarded, and scientists will have to turn to more radical new physics explanations. Regardless of the outcome, we are closing in on an answer. The significance of this quest extends far beyond the dispute over the Hubble constant's value itself. It concerns scientific methodology and our view of the universe. It reminds us to maintain humility in our cosmic quests. No matter how powerful our telescopes, they peer into the deep sky from a tiny blue planet. Our perspective is inherently limited. True scientific courage lies not only in constructing grand theories, but in daring to question our most fundamental assumptions, including whether our place in the universe is typical. From geocentrism to heliocentrism to the cosmological principle, human understanding spirals upward through constant self-negation. Discovering we inhabit a vast cosmic void may be the latest chapter in this river of knowledge. It is not regression, but progress. It reveals the universe's true structure to be more complex than our most sophisticated simulations, and more magnificent than our boldest imaginings. For every soul who gazes upon the stars, this story holds profound lessons. Science is not a closed book inscribed with absolute truths, but a dynamic, self-correcting process of exploration. Contradictions and crises are not failures of science, but catalysts propelling it toward deeper understanding. The Hubble tension and its potential solutions perfectly showcase science's allure in navigating uncertainty. We stand on the threshold of a cognitive leap. Next-generation observational data is about to flood in. It will bring answers, and perhaps new, deeper questions. But this is the essence of scientific inquiry, an endless journey, guiding us toward a truer, vaster universe. Our story begins with a seemingly minor discrepancy, an irreconcilable gap between 2 precisely measured numbers. It led us on a journey spanning 13.8 billion years of cosmic history. From the universe's initial fiery echoes to today's grand map of galaxy distribution, we have explored an incredible possibility. Our own Milky Way galaxy may not reside in a typical region of the cosmos, but instead dwells near the center of a vast cosmic void spanning 2 billion light-years. If ultimately confirmed, this discovery would represent one of the most profound paradigm shifts since Copernicus. Copernicus removed us from the center of the universe. Hubble revealed our galaxy as just one ordinary member among countless others. The cosmological principle teaches us that the universe is fundamentally uniform on large scales. Yet the discovery of the KBC Void introduces a new twist to this grand narrative. It tells us that even in a centerless universe, our local environment remains critically significant. We may not occupy a geometric center, but we reside in a metrically special location. This position shapes the universe we observe and influences our understanding of reality itself. This is not regression, but a more mature cosmological perspective. It demands we abandon the last vestiges of unconscious, self-centered assumptions. Honestly acknowledging our viewpoint is partial and biased. True universality can only be attained by understanding and correcting this partiality. This represents a deeper Copernican principle. Not only are we not at the center, we are not even in a typical location. What we observe is not the entirety of the universe, but merely a specific sample of it. This journey of scientific exploration itself is the most vivid embodiment of the scientific method. Science is not composed of unchanging dogmas. It is a dynamic, self-correcting process. Science becomes truly fascinating when observations and theories present irreconcilable contradictions. The Hubble tension is not a failure of cosmology. It is a sign of cosmology's vitality and ongoing progress. It compels us to re-examine our most fundamental assumptions. It drives us to develop more sophisticated instruments for deeper observations. It compels us to consider possibilities that initially seemed implausible with greater openness. The rise of the KBC Void hypothesis perfectly illustrates the power of Occam's razor. Guided by the principle that the simplest explanation is often the most desirable, scientists first explored what known physics could explain, rather than hastily invoking exotic new particles or undiscovered forces. This adherence to the principle of parsimony is the bedrock of scientific reasoning. It ensures our theories rest on solid foundations, rather than drifting in a sea of unproven conjecture. We now stand on the threshold of a defining moment. The next 5 to 10 years will be cosmology's golden age. A series of extraordinarily powerful observational tools is poised to transform our vision. The Vera Rubin Observatory will commence its epic decade-long sky survey, recording the positions and shapes of millions of galaxies each night. It will map the complete three-dimensional boundary of the KBC Void with unprecedented precision, precisely outlining the shape and density contours of this colossal structure. The Euclid Space Telescope has already deployed in space. It will measure the distances of billions of galaxies in the infrared band, probing the history of cosmic expansion with unparalleled depth. It will precisely measure baryon acoustic oscillations across cosmic epochs, testing whether the void distortion model holds at all distances. The Nancy Grace Roman Space Telescope will succeed Hubble and Webb, continuing to deepen our understanding with its vast field of view and high resolution. These facilities working in concert will provide a decisive test, either confirming the void hypothesis or definitively disproving it. If these observations confirm our predictions, if the Hubble tension does indeed vanish at distant scales, if galaxy flow patterns perfectly match void-dispersed expectations, then the lambda cold dark matter model will gain robust support. We need no new physics, only a wiser application of existing physics. Cosmology's standard model will weather its most severe challenge, emerging stronger and more reliable. If the observations contradict the void hypothesis's predictions, scientists will have to turn to more radical new physics explanations, such as early dark energy modifying gravitational interactions with dark matter. These currently fringe ideas will be thrust into the spotlight. Whichever outcome prevails, we will gain deeper understanding of the universe. This is the beauty of science. It guarantees we will always move forward. For each of us who gazes at the night sky, this story holds profound implications. It reminds us that knowledge is fluid, not static. Truths we hold as certain today may be revised or expanded tomorrow. This should not unsettle us, but liberate us. It means the universe remains forever filled with wonders waiting to be discovered. Science's greatest strength lies not in possessing all answers, but in its inherent capacity for self-correction. The Hubble tension demonstrates how a community of scientists confronts anomalous data. They first doubted, then puzzled, then debated fiercely. Ultimately, Through collective wisdom and effort, they approach the truth. This process embodies the core of the scientific spirit more profoundly than any single discovery. Now, you are invited to become part of this great exploration. Keep your curiosity alive and follow the new discoveries of these space missions. When the next major announcement arrives, you will grasp its profound significance. You will see the faint points of light in the night sky with fresh eyes. Each point is a galaxy. Each galaxy tells a story of the universe, and we have only just begun to learn how to listen to these stories. This journey is far from over. It may only be just beginning. As we probe deeper into the cosmos, more mysteries will undoubtedly emerge. Each answer brings new questions. This is the very essence of exploration, an endless journey. If you enjoyed this journey through the mysteries of the cosmos, please like and share this video with other curious minds. Subscribe to the channel and turn on notifications so you won't miss our next exploration. Whether delving into the heart of a black hole or tracking the traces of dark matter, science awaits our discovery, and the greatest revelations always lie ahead. Thank you for diving into the vast mysteries of the cosmos with us. Remember, questions never exhaust answers. They only lead to more. And that's precisely what makes the journey worth continuing. We may live within a vast cosmic void, but this realization isn't a wall isolating us. It's a new window opening before us. Through it, we glimpse a more authentic, more complex, and ultimately more worthy universe to explore.